Hello, it's Keith here, and this is lesson 2 of the advanced series of my Z80 programming tutorials. Now today we're going to be having another look at interrupts. We've had a look in the past in lesson 7 of the regular series, of the basic series, and we're going to cover again a little bit what we covered there, because last time we only looked at interrupt mode 1. Now there is 2 other interrupt modes, and we're going to look into them into more detail, and we're going to discuss interrupts again. And this is important because while what we learned last time was great for the Amstrad CPC, if we want to be able to use interrupts on any system, we need to really understand all the options available to us and how we can use those best on those other systems. Well, firstly, if you missed lesson 7, what's an interrupt? Well, an interrupt is where a device attached to the computer literally interrupts your program and says, hey, I want to do things. And depending on the system you're programming, what device will cause the interrupt, how often that interrupt will occur, is really going to depend on that system. But generally speaking, with regards to computers and game systems, you can kind of assume that the interrupt is going to happen during each screen refresh, or potentially multiple times per refresh. For example, the spectrometer occurs once per screen refresh at 50 Hz. On the Amstrad CPC, it's actually 6 times per screen refresh. But as a programmer, the main benefit of this to us is that we can time events. Now, in my last lesson, we actually looked at how to play music, and when you're refreshing your music, you have to update it at 50 Hz. So you really need to be able to use interrupts to allow your music to update in a continuous fashion. If you actually updated it once per screen draw, for example, of your program's screen drawing, then it might happen faster and slower depending on how much stuff was on the screen, and that's not going to sound very good in most cases. So by using interrupts, we don't have to worry about how long our program's taking to do its other jobs. We can just let the music update itself via those interrupts. However, while interrupt mode 1 potentially gives us the easiest way of doing this, there will be cases where that isn't an option to us, and we need to look at the other option. So anyway, let's have a very quick look at interrupt mode 1 first of all. I'll just move this out of the way, and let's get our program code in. So we're going to write a very simple program here, and we're going to do org and 8000, and I'm going to put this in IM1. We'll change to interrupt mode 1. Now there's practically all Z80 starting into mode 1, so this is superfluous, but I just want to show the command. This command says change your state to interrupt mode 1, and then I'm going to do a EI, and then I'm going to do turn interrupts on, because if interrupts are disabled then they won't occur. And then I'm going to do a halt, and that will pause until the next interrupt occurs. And then I'm just going to do inf loop and jump inf loop. Very flimsy, pathetic program here. I'm going to put a breakpoint here, and we're going to assemble this. And then we're going to do call and 8000. And you can see the program has started, and we'll just move this in frame. And so the halt command has occurred. And now this will continue, this halt will continue to occur until the interrupt happens. And I'll tell you now what happens when an interrupt occurs in interrupt mode 1. You can see IM1 here, interrupt mode 1, is it calls to memory address 38. So if I put a breakpoint here, you'll see very soon, there's our halt still occurring. Let's get rid of that breakpoint. We don't want to hear about that anymore. And there you go, we're now at address 38. So in interrupt mode 1, we can overwrite address 38 with whatever our jump to our interrupt handler is, and that will do our tasks like updating the music, flipping the screen, whatever we want to do on that timed event. But of course, we need to have access to a memory address 38 to do this. Well, that could be a problem. So apart from interrupt mode 1, what are the other options available to us? Well, there are 3 interrupt modes. There's interrupt mode 0, and there's also interrupt mode 2. As I've already said, interrupts are the devices connected to the Z80 causing events that they're demanding the Z80 process. Now what those devices are is totally unpredictable to us, and totally unpredictable to the Z80. So depending on the machine you're working with, we really can't say what that system's interrupts are going to be, so we have to talk in quite general terms. Interrupt mode 0 as a programmer, to my knowledge, is completely useless to us. Now what interrupt mode 0 does is the device is connected to the Z80. When the interrupt occurs, we'll send a single byte to the Z80, and the Z80 will process those as a command. Now, if you look at the Z80, a call, for example, takes 3 bytes, so you can't do a conventional call. And a lot of the commands, you could do an inc A maybe, but a lot of the commands aren't a single byte. And this is kind of where the RSTs come in, because they are a single byte call. And so I believe in interrupt mode 0, you would have your devices pushing potentially RSTs or maybe other commands that are 1 byte in size to the processor, which they would immediately execute. But I know of no case where a game system or a computer does this. So while I wanted to explain interrupt mode 0 to you today, just to be complete, I think it's completely useless. Now, interrupt mode 1 is the one we've just discussed. It's kind of the easiest for you to use if it's available to you. So you just write a jump or a few commands to the memory address hexadecimal 38, and they will occur every time the interrupt happens. And the entire frequency of the interrupt will depend on the computer you're working with, but it's generally going to be related to the screen refresh. So that's quite nice and easy. Now, but there's a problem with interrupt mode 1, as I've already explained. You have to be able to write to memory address 38, and there's a couple of cases that may not be very good for you. Well, firstly, what about if you need to do other things with that memory address? For example, the SAM Coupe, its memory banking basically splits the system memory in 2 parts, and its screen is 24 kilobytes in size. Well, if your program is at memory address 8000 and you need to load this 24K screen in somewhere, well, you're probably going to have to load it into the bottom area of memory, and that means your interrupts would be running part of the screen memory. Well, that's not going to work. So you really want to be able to move that 38 away from there. And also the ZX Spectrum, this is a real problem because the ZX Spectrum has a ROM bank at that low memory address. So you can't write or change memory address 38 at all. So what we would really like is a version of interrupt mode 1 where we can call a different memory address that's not in that first block of memory so that we have more flexibility. Well, does interrupt mode do that? Does interrupt mode 2 do that? Well, not really, but we can kind of make it do that. So what does interrupt mode 2 actually do? Well, interrupt mode 2 is a bit strange. It's again coming a bit back to the interrupt mode 0 concept, where the devices will send a single byte to the processor. And let's just have a look and just discuss what happens. So let's imagine we've got our device here, and the device is going to send a single byte, and that byte's going to be YY, just for argument's sake. Now, what the Z80 is going to do next is going to depend on 2 things. It's going to depend on that byte that the device sent, and it's going to depend on the contents of the I register. Now, if you remember, if you saw one of my previous sub-tutorials, there is a kind of rarely used and often free register called the I register here. And it's a single byte. It doesn't really do much, and it doesn't have a lot of options to us available. But this is where it comes in, you see. Now, when your processor is set to interrupt mode 2, if we just take away that interrupt mode 1 here, when your processor is set to interrupt mode 2, when the interrupt occurs, the bytes that the device send and the bytes in I, so if I equals XX, will be combined to create a memory address. So I will be the 2 high bytes, XX, YY. So this will become a memory address. What happens next? Well, from that memory address, another memory address is read. And then that memory address is called. So let's just think about this logically. Let's suppose I is the memory address 80, for example. Okay? So the memory address is going to be 80. And we can't really predict what the device is going to send, and this is true when you're actually using interrupt mode 2. So this could be 33, for example. Well, the memory address is going to be 8033, and then what's going to happen next is the CPU is going to pull 2 bytes from 8033 and 8034 as a memory address. And remember Little Indian, so 8033 will be the low part, and 8034 will be the high part. And then this memory address will then be called. This is quite strange. I know what you're thinking. This is getting confusing, and it's not really sounding very helpful, and it's not really clear how we can make any use of this. Well, let's just cut straight to the chase. I might make it really easy for you. When you're using interrupt mode 2, you kind of have to ignore all this. You don't know what data the device is going to send to you. You can't predict it. And so when you're using it, you actually just forget all of the logic. You forget all of the rules that I've just described, and you just go for the top level solution. And what you do is let's just have a look at this example here. This, if you imagine this is your memory map, when you want to use interrupt mode 2, what you do is you set your I register to a byte pair, which will be the top of a memory address, and then you fill the next 257 bytes with a single pair of bytes, and then if you imagine that, because whatever the device sends will then be read in as 2 following bytes, then a matched pair of bytes will become the memory address where your interrupt handler will start. So if I fill this entire range with 8 ones, then when the interrupt occurs, the memory address 8181 will be called. If I filled it with 20s, then 2020 will be called. If I set it to 55, then 5555 will be called. So all of the theory kind of goes out the window to an extent. Really, you're just filling whatever I is set to. You just fill the following 257 bytes with the same number, and then you put the start of your interrupt handler, or a jump to your real interrupt handler, at that byte that those 2 bytes combined together would make, at that address that those 2 bytes combined together would make. Now, I'm showing the example here of using the 80 to 8101 address range, of filling it with 8181 as the start of the interrupt handler. Now, why am I doing this, you might want to ask? Well, as I said, we can't use anything within the first 4,000 bytes, because that's going to be the ROM on the ZX Spectrum, and because, well, what's the point? If we can write to that, why would we even bother with all this? No reason at all. So why am I doing this? Well, with regards to the ZX Spectrum, there are certain memory addresses that are a bit of a no-go on the ZX Spectrum. I believe anything below 8,000, the memory address 8,000, doesn't work correctly with this because of the screen contention. So this is kind of the most reliable memory address to use for this kind of trick, and I can tell you very easily how I've confirmed this by asking people smarter than me. What I did is, if you've seen this rather fine Dizzy game here, the remake of Crystal Kingdom Dizzy, it's absolutely amazing. The graphics are brilliant. They've really shown off what the Spectrum colours can do. But this is a 128K only game, and that's kind of relevant. But they've used this memory address range, and from everything I've read online, this is kind of the rock solid memory address range to use for the ZX Spectrum. So yeah, I'd thoroughly recommend you check out this game, even if you're not a Spectrum fan. It's absolutely amazing work they've done. And I'll link it below. But yeah, if you're wanting to use a block of memory reliably for this kind of interrupt mode 2 handling, I would suggest you start with the 80,000 to 8101 range for your block of your jump block, as it were, and then put the interrupt handler at 8181, and that will definitely work on the Spectrum. That's what I do on Chibi Ackerman's on the Spectrum, and I believe that's what a lot of other people do as well. Now, that will leave a chunk of memory here completely unused, so what I'd suggest you consider using that for is actually your stack pointer, maybe, if you need a stack pointer somewhere, because it's got quite a bit of memory there, but it's going to be a bit like out of the way in the middle of nowhere, so maybe useful for your stack pointer, but of course that's entirely up to you. Okay. So that's a good way that we can set up a interrupt mode 2 to work with the system. Now, I did say that's the best on the 128K Spectrum. Of course, just that jump block alone is 257 bytes, and if we're then putting this weird stack pointer somewhere else where the byte pair matches, you're going to have a gap of space somewhere, or at least a jump block in some strange annoying place. So you are wasting, I mean, in this case, you're wasting sort of about 300 bytes here. You're probably thinking, well, is there any other options? I will be honest, there is another option that you do see online, and that is to use, there's a chunk of FF255 bytes in the ROM of the ZX Spectrum, and I've seen some people suggest that you use that and jump to FFFF as the start of your jump block, but from what I understand, that actually doesn't work reliably on anything except for the Spectrum 48K. So if you have got the memory, I'd strongly urge you to use this apparently more reliable version that, as I say, I've used it seems to work fine, and the gurus who made that Dizzy game seem to go with it, and they're obviously very skilled. So yeah, I'd suggest you go with this if you've got the option. And as I say, this does give you a way of getting out of that first half of the memory banks, which on the Sam Coupe will potentially be more useful to you for screen memory or something. But anyway, so that's the theory of how to use interrupt mode 2, and that's the theory of the useless interrupt mode 0. Okay, so let's actually have a look at some source code that is going to make use of interrupt mode 2. So what we've got here, you may not recognize it if you've not looked at my previous lessons. This is an Amstrad CPC example because, as I've said before, when it comes to theoretical stuff, I do it all on the Amstrad CPC because I find WinApe to be the best easy debugger assembler for beginners. So if you don't care about the Amstrad CPC, just ignore what this is doing. But basically, it's taking advantage of the CPC's as I said, the CPC has 6 interrupts during the screen refresh, so we can change colours at 6 points, and if the screen changes colour lots of times, we know the interrupt handler is working. But I've removed the code commenting because really we don't care at this point about that. What we care about is this new bit up here, which is as you can see here, going to use interrupt mode 2. Okay, so let's have a look at this new code and let's see what it does. Well, the first thing you should notice is we're starting at memory address 8000, and that's just kind of the common thing that my examples all do. We always start at 8000. Now we're going to use 8000 for our jump block, if you think here. So, well, what are we going to do about that? Well, what we're going to do is we're going to create 512 bytes of blank space, and we're going to jump over it. So effectively, there's a big gap here that we're going to then replace with our interrupt mode 2 jump block that will do the work for us. So we've just skipped over it. At first the program call will hit this, then jump to here, and then this will never be called again, so we can do whatever we want with this space. And what we're going to do, we're going to turn interrupt off because we don't want anything weird happening while we're messing. We're then going to put the byte C3, which is the jump command, at memory address 8181, which is of course here. I'll just move this over here so you can see this. So we're now defining this jump block here. So we put our jump in. Oh, that didn't work very well, did it? Let's get that out of the way. So we put in our jump command here at 8181, and then we put the address of our actual interrupt handler here into the next 2 bytes. So that will just, every time 8181 is called by interrupt mode 2, we will jump to our real code down here, which is going to do our color effect. Okay, so next what we want to do is we want to fill all of this area with 8181s, and we do that with an LDIR. So we set the first byte to 81, and then we fill the next 256 bytes, creating a bank of 257, because it's always going to load a pair, and we can't predict what memory address it's going to read from, so we have to fill this whole range. You can't even predict if it's odd or even, you've got no choice. So we just have to accept that and bite the bullet and use up all our memory, unfortunately. But that's the way it is with interrupt mode 2. So we're now filling the range. Now that we've got this created, we're able to use interrupt mode 2. We now have to get the memory address of the start of the block into I. Remember, we have to set I to the first half of the address that will be used. So let's put that there. So we have to load it into A first and then shift it into I. Now that I is ready and our jump block is ready, we can switch interrupt mode 2 on. And just for good measure, I'm actually using this chunk of area as my stack pointer, just because why not? Now you'll notice stack pointer is pointed to 8181, which is the start of the jump block, but every time you push onto the stack pointer goes down first, so we're not overwriting our jump block or anything with that. Right, well, we're good to go. So we just turn on interrupts and go into our infinite loop. Well, very good. So let's move this into here. Let's get the Amstrad back. If we do our assemble, no bugs, that's good to know. And we do call and 8000. And well, that's exactly what it used to do. So, well, maybe I'm cheating you. Maybe we're not really in interrupt mode 2. Well, let's pause. Let's have a look. Well, you can see IM is now 2. And if that's not enough, let's go to 8181. Let's go up here. You can see the stack has pushed a few random bytes on there. But if we put our breakpoint here, and we'll just scroll up as well, you can see this is the interrupt mode 2 jump block that I mentioned before. So if we now close here, you'll see we're now hitting 8181. And the reason for that is because interrupt mode 2 is doing exactly what I said it would. Well, there we go. And really, that's all there is to interrupt mode 2. I mean, it can be quite daunting if you look at the theory of it, but really, you don't really need to worry about it. All you need to do is just accept, if you will, that this is the way to use it in most cases. If you can't use interrupt mode 1, if you need that bottom block to be available for other things, or you can't write to it at all for in the Spectrum's case, then just take this as the sort of template way of using it, and it will work just fine for you. And then after that, you don't really need to worry about it. And it's honestly, it's not slow. When I somehow got it in my head originally that it was going to be much slower, but it's not slow at all. It's no slower really than interrupt mode 1. So interrupt mode 2 is a great solution for you to give you that extra flexibility. And when I started writing Chibi Akumas for the Amstrad CPC, I didn't understand anything about interrupt mode 2. I didn't worry about it, didn't care about it. And then when I started looking at the spectrum, I was just like, oh my god, what am I going to do? How do I do this? And I was reading interrupt mode 2 and scratching my head thinking this is going to be a disaster. But it's after you get past the pain of the working out what the meaning of it is, it's very easy to use, no problem at all. So this is the example of how to use it. You can check out my website for the documentation on it. We've just really covered the same content today. Now, what I'm planning to do next time is I'm going to make this even easier for you. I mean, I've shown you how to use it today. Of course, you can just copy and paste my code here. But what I've got for you next time is I've got a kind of template interrupt handler, which you can just get to do all the work for you. It will switch. It will work in interrupt mode 1, interrupt mode 2, just as simply as each other. And even better than that, what it's going to do is, I don't know if you've seen my lesson on how to use the stack pointer for fast reading and writing, but I told you at that point, if you're going to do this, you've got to disable interrupts. And that could cause you problems if your music's playing and it's slowing down, or if you're trying to do these raster effects. They're very, very time sensitive. So you may be stuck between, I want to use this stack pointer for speed, but I can't turn off interrupts. And the example I've got next week is going to show you a way that you can basically avoid having to stop interrupts, or at least stop them for so long, misuse your stack pointer for whatever you want, but still have the interrupts firing at the normal times. And it's going to do all the work for you. So we'll go through the theory, but you can just chuck my code into your own software and it will do all the work for you, whether you want to use interrupt mode 1, interrupt mode 2, whether you don't need to be misusing the stack pointer, or whether you do. So please follow me, and please tune in hopefully next week for that. I hope you've enjoyed today's lesson. I think I've enjoyed explaining interrupt mode 2 because, as I say, it was so daunting to me at the start, but really it's very simple. Anyway, thanks for watching and goodbye.